So hello everyone. In this particular session, I'll be explaining a very simple code which will toggle the case of any given string. Now, what do you mean by toggling the case of any given string? If we take the example of this particular string, that is nothing but hello world. Here, except for the very first letters, all other letters shown here are in lowercase, while the first letters are in uppercase. And these are numbers, so lowercase, uppercase doesn't apply to numbers. So here, what our code will do is, it will toggle the case. What does that mean? Wherever you will find the letters in lowercase, they'll be converted to uppercase, while the letters in uppercase will be converted to lowercase. That is, the result that we expect is okay. Now let's see how we can do this in assembly language. For that, first of all, you should know something about ASCII values. What do you mean by ASCII value? ASCII stands for American Standard Code for Information Exchange. Now what is this ASCII? ASCII is nothing but character encoding standard that represents text in computers. Okay, and this particular standard uses 7 bits to encode any given character, okay, because of which it can represent in total 128 values. We know it can have max 128 values. So what are these 128 values? ASCII value starting from 0 to 31 will represent control characters. What do you mean by control characters? Examples for that would be new line, tab, etc. Then we have values ranging from 32 to 126, which represents our letters, digits, punctuations, etc. And then we have 127th value representing delete. Okay, and why are we discussing so much about our ASCII values? Thing is, in case of ARM, strings are nothing but arrays of ASCII bytes. What does this mean? If you check the memory, if you consider this exact string, in the memory, each of this character will be stored as ASCII value. And now if you consider the individual characters shown here, okay, each character requires a minimum 7 bits, okay, and one location, if you consider in the memory, it can store up to 8 bits, okay, because of which each of this character will occupy one location or 1 byte of memory. Okay, that's how this particular string will be stored in the memory. Now, since we know how it is stored in the memory, now to understand more about the logic, you need to know something about the actual ASCII values associated with letters. That is, if you consider small letter A, okay, its ASCII value in hexadecimal is 61, which in binary is nothing but. At the same time, if you check capital letter A, okay, its ASCII value is nothing but 41, whose binary value is nothing but, okay. Similarly, the ASCII value of Z is nothing but. Why exactly am I giving the binary representation of the ASCII values of these letters? So that you can notice one important difference between these character values. That is, if you check the 5th bit position, that is, this is the 0th position, 1st, 2nd, 3rd, 4th and 5th, okay, that's the only bit which is different between the lowercase character and uppercase character. Same thing you will notice here. All the other characters are same, but the 5th bit position have complementary values. To be specific, the 5th bit of lowercase character is always set, while the uppercase character is always clear. This is the main logic that we'll be using in our code in order to flip the case of a given string character. Okay, so if somewhere in the code, as you can notice here, a particular bit is flipped, that is because just by changing the given bit position value from 0 to 1 or 1 to 0, we can actually toggle the case of that particular character. One more thing which is important for you to know is the letters have ASCII value in the range 61 to 7A and 41 to 5A. That is, 61 to 7A are range of ASCII values for lowercase characters, while 41 to 5A are nothing but the ASCII values associated with uppercase characters. Other than these ASCII values, all other ASCII values are irrelevant to us. What it means is those other ASCII values must be skipped because we don't want to change anything associated with any other ASCII values other than the ones associated with our letters, because case is something associated with letters. Now we'll come back here and try to understand what exactly is happening. Area here is nothing but an assembler directive which will define a section of memory to store this particular information. Toggle is the name given to this particular section of memory, and code indicates that we are actually storing instructions and not just data. Read only because we don't want any modification to be happening to this particular code. Entry indicates where exactly execution starts. That is, the very first label that is seen after entry is a location where the execution will start. Okay, and again here you will see same area which will define a section of memory, store this particular data, and because of which we have written data here. You don't have to again create something like this. It will work even if I remove this part. Both will work, and SRC and DST are labels here. Okay, but one thing you notice here is something called area followed by some name followed by data and read write. What is data here? Data here indicates that this information written here is not instruction but it's actual values. Okay, read write because we should be able to modify this particular content. Space is an assembler directive which will ensure that 32 bytes of memory is reserved so that we can store our final result here. Here if you see, you'll see something called DCB, which is define constant byte. Okay, that is because each character here will require 1 byte of memory so that we can store it. Okay, and here comma 0 because it is a null-terminated string. It's a common practice to indicate the end of the string. Align here ensures that there is no memory alignment issue. Okay, specifically because we have used DCB here, and end here indicates the end of source file. Now we'll come back here. What we are doing here is the address associated with the label source and destination is stored in registers R0 and R1. Okay, this is our main loop. Okay, wherein the very first thing that we are doing is we are checking if we have reached the end of the loop. That is, here if we see, okay, we are loading a byte of data from the location pointed by R0. What is it? It is this particular location. Okay, or it's the address associated with this label. When I perform LDRB R2 comma content of R0, what will happen is the very first content, that is ASCII value of letter H, is stored in register R2. Okay, then we check whether it is actually 0. 0 is the ASCII value we'll obtain only for null character. We won't get it for any of other string characters. So until we reach this particular value 0, we know we have not reached the end of the string. So we'll have to continue checking. But if we did reach the end of the string, then we'll have to branch to finish. Branch if equal, we'll check whether Z flag is actually stored as 1. and this will become true only if R2 is equal to 0, because in that particular case 0 minus 0 will actually be 0, because comparison always performs subtraction. And if 0 is a result of that particular subtraction, Z flag will be set as 1. If that is the case, we'll branch to finish, where we are storing R2 as actually 0, and this particular content is stored in the memory location of R1. That is because we have already reached the end of the string, and we are just making sure that our final result that we are storing, okay, that is our final string being stored, is also null terminated. And if that is not the case, then we are performing the remaining operations. See, the first thing we are doing is we are performing OR operation on the content of R2. Let's assume R2 is holding the ASCII value of H. What is the ASCII value of H? It is nothing but 48. How will you write it in binary? 0 1 0 0 and 1 0 0. By performing OR operation with the value 2 0, what exactly are we doing? The result of this particular OR operation will be 0 1 1 0 and 1 all 0, which is nothing but 68, and this is nothing but the ASCII value of the letter small h. So what do you think is happening in this particular case? We are actually converting all letters to lowercase. Okay, now if the given character is actually an alphabet, then this approach is correct to convert everything to lowercase. But what happens if the given character is actually a number or any other character which is not an actual letter? For that we need to perform some checks here. Okay, now let's see what's happening there. If this is our string, our first work is to identify whether the given character is a alphabet or it is a number or any special character. To do that, what we actually perform here is conversion of all letters to lowercase, okay, so that the only possible values are from A to Z, that is the ASCII values 61 to 7A. If the given character that we converted to lowercase lies in this particular range, it means it is actually an alphabet. If the given character has some value less than A, could be 60, could be 59, could be anything lower than this, or it is greater than the small letter z, it could be 7b, 7c, anything above that, then any of these characters considered are not an alphabet, because these are the only allowed range of values for small letter A to Z. Okay, what that actually means is the given character is not an alphabet as long as it doesn't belong to this particular range. As soon as we identify that, what we have to do, we have to ignore whatever value we got after the conversion, and whatever original value we have extracted here, that should be stored in the final destination location. Okay, if that is not the case, that is if the given character actually belongs to one of these ASCII values, in that particular case we'll perform our flipping operation. Okay, and our task is very simple. We have to just complement the 5th bit position, and how we do that? By performing XOR with the value of 20. 20 means we are considering the 5th bit position. Okay, 0 and 2. As long as we perform XOR operation, it doesn't matter whether we are considering lowercase value or higher case value, it immediately gets flipped to opposite side. Why? Now let me consider the case of H to be more specific. We know has its ASCII value given as 48, and already we saw how by performing OR operation with 20 will get a value 68, correct? Now check what happens here. The ASCII value of small letter A is nothing but 61. What do you think happens here? This is small letter h, this is small letter A. Internally subtraction happens, result is nothing but 7, correct? But result is discarded. Instead, based on the result, CPSR is updated. What flags do you think will get updated? C will be set as 1 because there is no borrow generated. Because C, that is carry flag, is set as 1. When you check branch if lower, what this will check is, it will check the C flag. Okay, this particular condition becomes true if C equal to 0. But in our current case, C equal to 1 because it does belong to the range 61 to 7A. We'll check one more condition. That is, after this particular condition is checked, we will compare the value of H with the value of Z. That is, what will happen when you perform subtraction between 68 and 7A? You can clearly see that this value is higher than 68, correct? Because of which C flag will be set as 0, correct? And along with that, Z flag will be set as. What happens in case of branch if higher? This condition is true if C equal to 1, at the same time Z equal to 0. But clearly C equal to 0 in this particular case, because of which this condition also becomes false, which clearly means our value H lies between A and Z, and hence it is declared as a alphabet, because of which it requires the desired flipping. And what do you mean by flipping here? So now one thing if you notice here is, even if I am comparing the value of R3, here I am XORing the value of R2. What is R2 value? R2 is my original value. Okay, for H, my original value, that is ASCII value, would be 0x48, which is 0100 and 1000. Now because I am performing XOR operation here with 20, so this is what will happen. In case of XOR, only complementary bit positions will get the value as 1, all others are 0. So what is this? 68, and 68 is nothing but ASCII value of small letter h, because of which the final value that is stored in R2 is nothing but 68, and then this value of 68 is stored in the location pointed by R1. What is the location pointed by R1? It is my destination, and R1 address is incremented by 1, so that the first value will be stored in the form of small letter h, and then R1 is incremented so that it can point to the next location. Okay, then we are branching back to toggle, because we have not finished checking all characters and converting each character to the opposite case. And once all these steps are done, okay, we have reached the end of string, we'll then move to stop be stop, which is nothing but an infinite loop. Okay, now let's see how this particular code works. Okay, there are no errors, so we'll go ahead with debugging. So here, very first thing that we are doing is nothing but we are loading address associated with the label source and destination to register R0 and R1. Let's feed them in the memory window. Okay, now if you want to see the actual text, you will have to just right click and then click on ASCII. You can see hello world 2026 written here. You can see H and W are caps, all others are small letters or numbers. Okay, I'll just change it back to numeric value. My work is to copy this data and paste it here by making sure that all the case of the characters are toggled. The very first data is copied to register R2 as expected, and we check if it is already null character. In our case, that is not true. This is how the CPSR is updated. The Z flag is not 1, because of which branch won't occur. Instead, we are performing OR operation on the content of R2 and storing the result in R3. Okay, so after OR operation, what should be the result? R3 will get the value 68, and 68 here just represents small letter h, while 48 in R2 represents capital letter H, which is the actual value. Okay, so now when we continue, what will happen? We are comparing the given value, that is 68, the ASCII value of A. Okay, and the result of comparison will update the CPSR. Okay, as you can see here, Z is 0 and C is 1, because R3 is actually greater than the ASCII value of A, because of which this condition becomes false. This will be true only if carry flag is set as 0. Okay, so that jump won't happen. Instead, it will check whether given character is actually greater than Z. Here we are just performing subtraction and updating the CPSR. Checking happens here. Okay, now let's see CPSR getting updated. Yes, we can see that here. We can just ignore N for now. Z is 0, C is 0. Now because C is 0 here and Z is 0, obviously this branch won't happen. Okay, instead XOR will be performed, and what is the result of XOR? XOR will ensure that this 48 is converted to 68. That is, we obtain the ASCII of the lowercase h, and then we are storing it in the location pointed by R1, which is our destination. And if I change this to ASCII here, I can see the actual text. Okay, so one task is done and we are repeating the loop. Okay, so next content is taken here, which is nothing but our letter E in lowercase, and then we perform the same task. Okay, and so what will happen? Once all operations are done and flipping of case is done and we store the content, we'll see the value caps E or uppercase E. Okay, so let us continue this in the same way. Okay, and see all the characters getting stored here. If you consider this particular case, already hello is done. Next what we have is a space character whose ASCII value is actually 20. Now 20, if you consider here, it is not equivalent to null character 0, so that branch won't happen. But when ORed with 20, the result is 20 itself. So when I compare it with letter A, whose ASCII value is nothing but 61, it is less than that. So because of which this particular branch will become true. Reason for that is comparison will perform subtraction, as you can expect, and that will update the CPSR. Okay, in this particular case, what happens? C becomes equivalent to 0, Z becomes equivalent to 0. Okay, if C is 0, it means borrow is generated. That is because R3 is less than A. Okay, and because of which will branch to store character. This is done so that whatever manipulation we need to do in case of letters should not be done for any other characters or digits. So to differentiate that and to directly store the content of any other characters other than the letters, we have added this particular comparison. Okay. Same thing happens with respect to numbers. Okay, even they will remain unaffected. Okay, and since all characters are stored, lastly what will happen? There will be a jump to finish wherein we are storing the null character, and then we are jumping to an infinite loop. That's all about toggling the case of any given string.